Hey guys, welcome back for chemistry. You're here with Mrs. Mays, and today we're going to look at the relationship between solubility and temperature. So let's get right into it. First of all, we already know that increasing the temperature of a solvent could increase the speed of the particle movement inside that solvent. So all of the little particles are speeding up. This causes more of the solvent particles to essentially bump into the solvent particles, bump into the solute particles. This results in solute particles being able to then break loose and dissolve into the solution faster. So, aside from just increasing the temperature of your solvent, can you think of any other ways that we could get the solvent to bump into the solute more often? What do you think? Think about some other ways. Maybe we can make that happen. And here's what we know about solids that are dissolved in liquids. You've probably tried this before. If you have some tea and you stir your sugar into your hot tea, ask anyone from the South about making sweet tea. You can't dissolve the same amount of sugar into cold tea as you can into hot tea. There's a process here, an important process for making sweet tea. So solids dissolve more in warmer liquids. But if you're drinking a soda pop, that's a different story, right? Anybody ever had flat, hot soda? Kind of gross, right? It's not as bubbly because gases dissolve in liquids better when it's colder than when it's warmer. Yeah, you already knew that, didn't you? I mean, that's been your experience. Now think about what that means, though, for our waterways. Solids are more soluble at higher temperatures. So if the temperature of our rivers and oceans increases, that makes the solids, any contaminants like salts and fertilizers and things, they would be more soluble in those temperatures. Gases are more soluble at lower temperatures. So the higher you go up into the mountains, the colder and colder it gets. That means there's going to be more oxygen for the fish there. Some fish can't handle that amount of oxygen. But here's the kicker. The higher you go in the mountains, the lower the air pressure goes. And gases are more soluble at higher pressures. That's why your soda is pressurized. You open it and it goes psh, because it releases some pressure, right? Well, there's less air pressure in the mountains too. So it balances things out for the fish that are trying to get oxygen in those cold mountain streams. Fish like salmon and trout, they need that colder, high oxygen water. All right, now let's look at the solubility curve. Curve? What? Well, we are basically referring to a graph. The solubility curve is a line on a graph that shows the solubility of a compound at various temperatures. And each compound has a unique and different curve because of the way it dissolves in that particular solvent. It kind of looks like this. See, I have several different solutes, different salts shown, and some gases. Solubility is dependent on the temperature of the solvent. So what trends can you see on the graph? Look it over. What do you notice? All the solid lines are sloping upwards, positive slopes. All the dashed lines are negative slopes, sloping downwards. So how is the solubility of the gases and the solids different? Just like we talked about, right? They decrease for gases as the temperature gets higher, but increase for solids as the temperature increases. Some slopes are more steep than others. So if we stir the solute into the solvent, does that make you dissolve more of the stuff? What do you think? Actually, it doesn't really allow you to dissolve more. It just allows you to dissolve the substances faster. Increasing the temperature does, however, allow you to dissolve more solvent. And that's how we could get a solution to be supersaturated. If we heat it up, then we can get more solute in there than what normally would be able to dissolve. So here's how we would approach problems about solubility versus temperature. For example, what term describes 39 grams of sodium chloride at 70 degrees Celsius? So let's find our 70 degrees Celsius line and see how straight I can draw this line going up. There's my 70 degrees line. And I'm going to leave that there because all these questions have to do with what happens at 70 degrees. So find 39 grams. Here's 40. I want 39 just below it at 70 degrees, and that puts me right on the line. That would be called saturated because now we got to the maximum amount that we can dissolve at that temperature. So that solution is saturated. What if we had 30 grams at that same temperature? 30 grams would be like down here on the chart, right? Well, what do we call that? Right, unsaturated. We haven't quite gotten up to the maximum amount that we can dissolve. All right, then how about if we put in 45 grams? That's way up here on my 70 degrees, same temperature, right? So if I was way up there on 45 degrees, we'd have to call that super saturated. Now I have more solute in my solution than what I can dissolve at that temperature. So the solubility curve is a characteristic of that particular substance. Each substance has a different maximum amount that can be dissolved. It's called its molar solubility. And when you learn the solubility rules, you learn that some things have a very high molar solubility, like sodium and nitrate ions have high solubilities, almost always soluble, right? And some things tend to have very low solubilities, like when chloride hangs out with silver, mercury, or lead. The curves for gases will have a negative slope, whereas curves for solids have positive slopes. That summarizes what we just learned about solubility curve. Now let's see how we would apply this. An unsaturated solution means it contains less dissolved solute than the solvent can normally hold at that temperature. So it's anywhere below the line of saturation. That's going to be considered unsaturated. If I'm right on the line, then it's called saturated. But a supersaturated solution contains more solute than can usually be dissolved at that temperature. So that's anywhere above our line of saturation. And anywhere along the line is considered to be saturated. So now let's get specific. If I'm at 45 degrees, how much potassium nitrate will dissolve in 100 grams of water to form a saturated solution? So let's find 45 degrees Celsius. And here's my potassium nitrate line. So now I've got to read across. It's a little bit less than halfway between 70 and 80. So I'm going to estimate that to be about 73 grams of potassium nitrate will dissolve at 45 degrees Celsius. Okay, suppose we're at 60 degrees Celsius. We put 80 grams of potassium nitrate in 100 grams of water. What is the level of saturation for this solution? So here's my 60. Let's find the intersection of my 60 and my 80 grams. Whoops. Here's 80. Okay, are we above or are we below the potassium nitrate line? Goes along right here. Looks like we're well below it. So that solution is considered to be unsaturated. Finally, in our last example, how much sodium chloride is needed for a saturated solution? So we want to be right on the sodium chloride line at 75 degrees Celsius, and look out, 200 grams of water. Well, let's find out 100 grams and go from there. So 75 degrees up to my sodium chloride line, which is right on my 40 grams line. So if I can dissolve 40 grams in 100 grams of water, then how much could I dissolve in 200 grams of water? What do you think? Right, cross multiply or just, double it. That should be 80 grams of sodium chloride. And that's how we work with the solubility curve.